Hello, this is our final design review for our senior capstone project. We're team 2.
I'm Osvaldo.
I'm Nemo.
I'm Alan.
And I'm Kaylee.
So first and foremost, we want to thank our sponsor, Dr. Ian Yuan, pediatric anesthesiologist at Rady Children's Hospital, for giving us this project and helping us along the way.
So a little background on our project. As many of you know, a regional nerve block is a local anesthesia procedure that uses an ultrasound probe and a needle in the other hand to guide the injection near the nerve bundle. This procedure usually requires 2 people because the doctor has both of their hands busy. Somebody else needs to inject the anesthetic fluid.
So what we needed to do was find a safe and reliable way to allow a single person to be able to complete a local anesthesia procedure. And that's what this project does. We integrate a voice recognition software into an already established syringe pump.
Our project was tasked with the following requirements. For our voice activation system, we are required to reach a minimum of 95% recognition accuracy with a minimum of 1 second response time. It also was required to recognize 3 different injection profiles, which include 1 cc, 2 cc, or 5 cc, and for each command, respectively, have a tolerance of plus or minus 1 cc, and additional commands such as stop and aspirate. Lastly, for our voice recognition, it should be reliable amidst background noise. And for our mechanical system, our device was tasked with maintaining a safe injection pressure from 10 psi to 15 psi, be able to accommodate both 10 cc and 20 cc syringe sizes, and fit within this specific volume with a weight less than 5 kilograms, making it simple, portable, and easy to use. And for our second objectives, we were tasked with placing a pressure sensor with an over-threshold alarm and a customizable flow speed.
In the following slides, we'll go over the key design decisions for the control system, actuation system, mechanical syringe assembly, user interface system, embedded software, voice recognition software. So for our control system, we have a dual processor architecture with a Raspberry Pi 5 handling the voice activation software and the user interface, along with the ESP32 handling the controls for the motor actuation and the sensor feedback with the load cell, which will be monitoring the pressure, along with limit switches preventing the carriage from crashing and destroying itself. We also have an encoder for the volume tracking, and we chose a TMC2209 to make the operation quieter, along with making sure that the motor noise itself doesn't interfere with the voice activation software. We also have a usability of a microphone through USB, or alternatively, you can use Bluetooth devices.
Following our control system, we have our actuation system, which was compared amongst 3 different mechanisms that convert rotary motion into linear motion. So here we have our lead screw, belt and pulley, rack and pinion. They were all evaluated amongst cost and their pros and cons. As you can see, we went with the 200mm TR8x2 lead screw and NEMA 17 stepper motor due to its precision of 1.2 micrometers per microstep, meaning minimal backlash and being able to deliver accurate injections within plus or minus 1 cc. And with our stepper motor, its compact and encoder feedback allows proper linear displacement among the plunger axis. Now for our mechanical syringe system, which links our controls and actuation systems. So here we have an annotated CAD of a mechanical syringe system, and 3 key design decisions were made making this. So our first is our carriage. So our carriage consists of a carriage, load cell, and load cell plate in order to detect pressure during aspiration and injecting procedures. Our second is our plunger sliding clip, which is meant for alignment and for security onto the load cell. And our third and final decision was our 20mm syringe mount and 10mm adapter in order to ensure that the syringe barrels are properly aligned on the same axis as our load cell. And so for our next slide, we have our actual mechanical syringe system. So here we have our three key design decisions as mentioned. We have our carriage with our load cell, along with a load cell plate with that blue 10 milliliter plunger flange attachment. And we have our 20 ml attachment along with our 10 ml barrel flange attachment for our 10. So as you can see, they were all incorporated in our design.
So here's some of the main pages that the doctor would come across while using the application on our device. So the first one they get lit into is the parameters page. Here they can choose from the syringe size, the manufacturer, aspiration time, injection speed, and the pressure threshold. Once they're satisfied with the parameters that they chose, they put confirm parameters, they get led into a calibration page. Here they can manually adjust where the carriage is, just to be able to properly mount the syringe. And this was our key design choice because we used to have a little rotary encoder, which is like a little knob. And switching from that to this makes it a lot more intuitive and way easier to control, especially for precise like micro adjustments. So once the doctor is able to confirm the syringe, they get led into that final page, which is about how the procedure looks. That's when the page, the voice activation software actually opens up and starts taking in commands.
So as previously stated, the Raspberry Pi is going to handle most of the higher level control, everything user facing, for instance, the UI and default settings and then the voice commands. The ESP is then going to receive commands from the Raspberry Pi through its UART connection. The commands are going to look like this: inject, aspirate, stop, status, and then it's also going to come, the inject commands come with the syringe size and then the volume that's supposed to be dispensed. The ESP then receives these commands in plain English, parses them, and then decides what to do. So for instance, in the inject case, it will take the syringe volume here, and then it also gets the area of the syringe and then the volume it's supposed to inject, and then it translates that to a linear distance. And then through some math with the encoder and the lead screw dimensions, it translates that linear distance to the encoder steps that it's going to send to the motor. The ESP handles all this, but it also handles the sensor feedback. So this sensor feedback includes things like volume and pressure, and then those values are handled and calculated within the ESP just in case it goes over the pressure threshold, and then those values are relayed back to the Pi to display to the user. So the second part of the embedded software that we worked on was everything behind the scenes that takes care of the safety control and the motor control. So as previously stated, the Pi is handling all the upper level things, but all of the safety mechanisms are mainly handled on the ESP. So for instance, a few things that we've done to increase the safety and reliability of our system is that we have a state machine. Basically what that means is that at all times, the machine will be out in a state. These states include idle, jogging, homing, injecting, aspirating, fault, and disabled. These different states decide what commands and what actions are allowed during their states. For instance, if something is currently injecting, it's not accepting more commands unless that command is to stop, for instance. The big one here is false. So if it is in a fault state, it's going to lock out all other commands until that fault is resolved. So you can see this in, for instance, when a limit switch is hit, that creates a fault state and it won't release that fault state until it backs off the limit switch. Pressure also works like this. If the pressure calculated on the ESP exceeds the pressure threshold, which is usually 15 psi, it will stay in a temporary fault state until the pressure falls back down, and then it goes back to idle, and then it will then accept more commands. A neat process we're doing with the stepper commands is that they work in pulses. So it sends a pulse to the motor controller to tell it to move a little bit, and then it checks if the state's still valid, and then it moves a little bit more, and then it checks if the state's still valid. We can't perceive that, but it gives the system time to stop the motion immediately, just in case there is faults. This is also all the motor control is done what's called open loop, which means that if the encoder and the expected distance are different steps or different distances away, it doesn't immediately do anything to correct it, but if this discrepancy gets too big, then it will put the machine in a fault state. And that's all to make sure that the system is running smoothly, but a lot of this is also not as strict as it could be, so the system can run smoothly and doesn't interrupt the operations. So moving on to our voice recognition system, it works based off of a 2-command system. So first you need to input a wake word command. This is like saying, hey Alexa. This primes the system and then starts listening for any other commands. Once it hears the wake word, then it can start listening for the actual commands. These commands are like the eject, the aspirate, the stop. It has a 5-second window to find that command. And then if it hears that command, it then parses it into a string that the Pi sends over to the ESP, and then that's how the motion happens. So under ideal conditions, we've had 100% success rates for the wake word plus command recognition, so the full voice recognition pipeline. These ideal conditions are around 40 decibels, which is basically a quiet room, and the mic is right on the person. We'll talk about it later, but we also seen diminishing results with louder environments. But it is noteworthy that we've reached the functional requirements.
So here's kind of a description of our final design choices. For the voice operation system, we thought it was best to integrate it onto the touchscreen itself, and it is able to support the commands that we need, such as the aspirate, inject, and stop. And then the precision injection system, we have that stepper motor along with that lead screw mechanism that is able to deliver controlled syringe plunger movement that is both compatible with the 10 and 20 milliliter syringes. And lastly, we have their safety monitoring features, which is able to do live tracking of the pressure, the volume injection, and the battery status. And we also have the limit switches on each end so that we can prevent any damage done with the carriage.
Okay, so now for a review of our hardware performance volume. So we had a total of 12 trials, 6 trials for our 20 milliliter and 6 trials for our 10 milliliter, meaning 2 trials each for each respective injection profile. So our 1 milliliter, 2 milliliter, and 5 milliliter. As you can see, we have a 100% pass rate, which means that all trials fell within our plus or minus 1 cc tolerance. In addition, our 20 milliliter syringe had an average of 19.57 cc injected, and our 10 milliliter syringe had our average of 9.65 cc injected. The max error across all our trials was 0.6, which is pretty small and below our threshold, which is really good. And we conclude that this really small error could be due to the plunger stiction and our lead screw backlash in our actuation system.
Now for our pressure trials, we saw that we had a peak pressure of 9.8 psi across both syringe sizes. Specifically for the 20 ml syringe side, the max range was 8.1 to 9.8 psi, and the mean was 6.3 to 8.6 psi, while for the 10 ml syringe, we had a max range of 7.7 to 9.8 psi, and for the mean, we had a 6.1 to 8.5 psi. All these tests were conducted alongside a pressure transducer to provide a more comparable and reliable data set. With that being said, we were able to conclude that the load cell error consistency was small and positive, ranging around 0.11 to 0.23 psi.
So to test our voice recognition system's success rate and its latency, we had multiple trials where the mic was on the person, and then to test its success rate, we tried various background noise levels. The 40 decibels is a quiet room, 50 decibels is light chatter in the background, 60 decibels is loud conversation, and 70 decibels is a loud room. As you can see, we had 100% success rate when in a quiet room. It was very, very responsive. The system worked really good when it was in a quiet room. When there was background chatter at a low level, we still saw very good results, but sometimes if the level in the room would get a little bit louder than the person talking, then you would see some faults. Once the level of the background noise in the room reached the level of the commands being given, the system started failing a lot more. As you can see, it's only around 50% successful at 60 decibels, and at 70 decibels, it's only 25% successful. So a clear result we can see is we have diminishing returns with increasing background noise. So for the latency, our goal was less than 1 second response time, and we cleared that very well. We were around 0.8 seconds at maximum for the response times. It is important to note that the response times differ between the different commands because of a system we have in place that preemptively starts the motion if it hears a partial command. For instance, if it hears inject, it will start the motion, but if it hears the rest of the command, like inject 2, it will then finish that command and go that specified distance. It is important to note too, we saw no false positives throughout all of these tests, meaning the system is very safe towards not engaging when it's not supposed to engage. We also didn't have any missed commands. So after the wake word was initiated, we always had successful follow-up commands, which is the intended performance of this system.
So some remaining questions and concerns we have right now is that the voice recognition software kind of begins to decay at higher noise levels, making it a little less reliable. The next thing on our list is the pressure calibration, as the load cell consistently shows a positive offset, which means that the calibration most definitely needs further refinement to meet the expectations under clinical conditions. And lastly, the pressure is consistently below the green zone as well. It should be constantly in the 10 to 15 psi range, but it's always below that. And that's likely due to our testing being without tissue back pressure. So we would need to do further validations under clinical loads with the tissue back pressure or something closely related to a simulated trial.
So for future recommendations, we suggest getting a custom PCB to consolidate the electronics onto one board. Another suggestion is to get a sealed and sterilizable enclosure to prevent water or any other liquid ingressing into the electronics and making it easier for the doctors to sterilize the overall device. Another suggestion is to make the syringe mounting more intuitive so that it's also easier to mount and quicker to mount the syringes.
So we have the two different syringe sizes. We have 10 milliliters and then 20. We're going to do the demonstration with 20 milliliters. So you pick the proper attachments. This one's for the 20. So you snap that on. And then you're going to go here to your parameter screen. We can select the syringe size of 20, and then everything else we're going to keep default for right now. So when we confirm parameters, this is when we try to load our syringe. Here, I need to jog it a little bit forward to get in place and then stop. And now you can load the syringe. Put the attachment, and then we're just gonna inject the fluid into a cup. So you confirm the syringe is mounted, you tell it how much fluid you have in it, and then it'll prime. This priming process is gonna move it forward so it hits the 20 milliliter mark here, and then it gets a baseline reading of the frictional forces. So now we can start the actual injection process. So before the injections, we have to aspirate. Jarvis, aspirate. So it'll pull back a little bit. Here you can't really see anything because it's not hooked into anything, but it will move back for a set amount of time. Now we can start the injections. Jarvis, inject 2. So here it's moving forward 2 milliliters, and you can see on this notch that it's now at 19 because we aspirated 1 back. So then just to do a longer injection, we can inject 5 milliliters. Jarvis, inject 5. Here our pressure readings are pretty stable because it's there's no back pressure, but this is a live pressure reading. And you can also see the live injections happening here. And then now we're at 7 milliliters injected. Yeah, so let's say we finish the procedure. We're done, that's all I wanted to do. You would end procedure. You remove the syringe first. Now that the syringe is removed, you press the syringe remove button, and it's going to move back and home. Now as the carriage approaches the back, it's going to hit one of these limit switches. And then once it does, it'll immediately stop and then start moving back towards the center so it's easier to reload. So let's say we have to do more injections now. You can go back and just basically repeat the process. Okay, so the other tabs here we have functionality for different microphones. You can either use the built-in microphone or you can connect to Bluetooth. Here we have our thresholds for the voice sensitivity. Right now, these are the default settings. So the wake word will have it's better to have a higher threshold than a lower threshold, so it doesn't have any false positives and accidentally pick up background noise and think you're setting a command in. But if the situation calls for it and it's a noisier environment, sometimes you can lower the sensitivity to get a more responsive wake word. Same thing with the command threshold. This threshold should work pretty well on default, but again, you can adjust it based on your environment and practice. We have the testing screen where you can test out how responsive the voice recognition is if you need to practice in like a noisier environment. Here you can see Jarvis, stop, and it'll count up your commands. And here's a help screen, basically just a little user manual to go over all the commands. So now we're going to demonstrate the procedure with the 10 milliliter syringe. It's almost the same setup. You just have to find the specific backing for the 10 milliliter syringe. It should have this little flap here. You line that up with this back and snap it in the same way. You should hear a click. And then the difference here is that this one also comes with an extra attachment. So here we select syringe size 10 milliliters. It's already selected. And you go to confirm parameters. You can slide this in, and then you see that this is misaligned right now. I need to move the carriage back a little bit. And then it should fall into place. We hit stop, and then it inserts just like that.